All right, everybody, welcome back to CS 125. It's a beautiful day here in Champaign. I hope it's beautiful where you are. I've got the cat with me right here. Going to help me out in today's class, mainly by sleeping on my computer and making it warm. I think she likes it on there because it gets warm. All right, so our topic today is we're going to finish up talking about recursion, and we're also going to look at sorting, which is a topic that is fun because it brings together a lot of what we talked about this semester. Algorithm analysis, which we talked about recently, we'll get back to that. Different approaches to solving the same problem. So sorting is a fun problem because it's conceptually easy to understand, but there are a lot of different ways to approach it, including apparative solutions that we'll look at, recursive solutions that we'll implement together. Sorting algorithms also tend to have really interesting trade-offs between best case versus average case versus worst case behavior, runtime in terms of how much memory they use and things like that. And so sorting is a topic that we're going to slow down and really enjoy together for a couple of classes, looking at a couple different sorting algorithms. We also have a chance to do some more sorting algorithms next week in lab. But this is something that we'll set up toward the end of class today. But for the beginning of class, I want to go back and return to a problem that we started setting up. And actually, we got through this together, but I want to look at a different way of doing it that exploits a new way of building binary trees. So remember last time, toward the end of class, we looked at how to search through a binary tree. And this is another place where we're going to apply the same three principles that we've used when constructing recursive solutions to problems in the past. The first one is we're going to have to identify a base case. So the problem here is that I have a tree that contains values, and I want to write an algorithm to return whether or not a particular value exists anywhere in the tree. And so here, my base case we identified was actually a little bit nicer than this. So the base case where I'm actually going to stop is the case where I've walked into an empty tree. Because an empty tree will never will never contain the value I'm looking for. It's empty, so it doesn't contain anything. The recursive step, as in many of the tree-based problems that we've looked at, is splitting the tree into a right subtree and a left subtree and looking at those separately. So if I don't know where the value is, how do I make the problem smaller? Well, I don't know how to search the entire tree, but I know that if the value exists in the tree, if it exists in my left tree, then it exists in the tree. If it exists in my right subtree, then it exists in the tree. And if it doesn't exist in either one of those, then it doesn't exist in the tree. I also have to remember to check myself, the node that I'm currently examining. So the recursive step here is pretty similar to us from the past. And the way that we combine results here is a little bit different, right? In the sense that, at any given node, there are three places where the value could be. It could be at this node, or it could be in my right subtree, or it could be in my left subtree. And the way I'm going to combine results is actually using this logical AND operator. So here was our normal tree class, and I'll just sort of go through this quickly because we did complete this at the end of class last time. So as we do typically, this is sort of a setup for a little bit more of an interesting problem that we're going to approach on trees in a few minutes. So here I have my typical approach where I have a public function that's part of now the public API for this class that takes a value to search for. And this function's job is to return true if the value exists anywhere in the tree and false otherwise. Okay, and so what we're going to do is we're going to override search with a private method that takes a similar value parameter. It also needs to know what to look for, but it also takes a node to look at. And that's the node that we're currently examining. And this is what we use both to make our recursive calls, but we also use it to bootstrap the process by calling it on the root node. So here what I'm going to do is I'm going to return the result of calling my overloaded search method, which takes two parameters on the root node. Now somebody asked last time, I think, about, why do I do this? And the reason is, the tree class that we've created, if we look at how it's structured, this node class is private. So nobody outside the tree class is actually able to use this node class. the tree's API, or its interface, remember every class in Java has an interface, even if it doesn't declare that it has an interface. The interface is the set of public methods that you can call. So I can add values to this class. That's part of the public interface. There's an add function that takes an object value and puts it into the tree. And I can also print the tree. That's another method that I can use. And now I'm providing this search method. So someone who's using this tree class is not going to know anything about that node data structure. That's internal to the tree. What it does know is it says, hey, I put a bunch of values into this tree and I can't remember if this value is in there anymore, so could you search for me? And that's what we're doing right now. So we don't want the caller to have to provide a node reference as part of the arguments. We know where the root of the tree is. That's another private member of this class, right? The tree class knows where the root is, and that's what we're going to use to start our search. So at any given node in the tree, our algorithm here really has, again, 3 steps. The first is the base case. So the question is, have I walked into an empty tree? And the way I check that is I say, if current is null, then I'm going to return false. So if current is null, that means that this tree that I arrived at is empty. It has no nodes. An empty tree does not contain the value that I'm looking for. I know that. So this is the simplest possible problem that I've produced where I can solve the puzzle right away. Right? And this is possible, right? So if I create an empty tree and I don't add any values to it, then the root node is null. So it's possible that if I search for a value in an empty tree, what's going to happen is my search method, my public search method is going to call my private search method. It's going to pass the root value, which is null, and I'm immediately going to return false. Okay, so that's the right thing to do. This also allows us to walk off the sides of the tree and off the bottom of the tree safely into trees that are empty, which simplifies the rest of our code. So now there are 2 other parts I need to do. I need to look at the recursive step, so I need to make the problem smaller, and I need to combine the results. So remember, there are 3 places where this value could be, and the order in which I search for them is actually pretty important. So the first place I want to look is this node. So does this node contain the value? And so what I'm going to do is I'm going to return the result of looking in 3 places. The first place is this node. So I say if current.value equals value. And if I allowed null values to be put in this tree, I would have to be a little more careful here. But right now I'm not worried about that. So current.value is not null, so I'm essentially saying if current.value equals the value, then I'm done. Then I found the value, and I actually don't need to look in the rest of the tree. I don't care. This is not counting the number of times that the value appears in the tree. It's just returning true if the value appears anywhere in the tree. If it doesn't appear at this node, there are 2 other places I need to look. I need to look in the, and Traversal is going to mad at me if I don't do this properly. I need to look in the right subtree, and I need to look in the left subtree. And I'm searching for the same value, so I need to pass the same value to my call to search the right subtree, and the same value to call to the call to search my left subtree. So this line, this single line, is actually doing both the recursive step and combining the results. The recursive step is look in the right subtree and the left subtree. Combining results is using this logical OR operator. And so now if I run this code, it's mad about, sorry, there's tab characters here. I don't know where those came from. I should fix this. All right, there we go. So this seems to work, right? It's able to find values. If I have it search for a value that doesn't exist, it should return false. If I have it search in an empty tree, it should return false. If I can search for anything in this tree, my tree can contain, either, sorry, check style. My tree, in this case, is built of integers, so strings are going to appear in the tree. So this all works okay. All right, so again, this is just review from last time, a little bit of a warm-up to what we're going to see. Now, one of the things that we talked about last time is this idea that, if the value is not in the tree, or even if the value is in the tree, I end up having to look in a lot of places. So you might stop and kind of do a big O analysis of our tree search algorithm. So the question is, what's the best case performance of this algorithm? And there are some times where the node I'm looking for is the root node. And then I'm only going to look in one place. And again, let's put this count variable back here. So I'm going to do public static int. Well, you know what? I'll make this an instance variable. Public int count. when I search, I'm going to set count equal to 0. And then every time I visit a node, I'm going to say count plus plus. And now when I get down here, what I can do is I can say not only print the result of the search, but I can print the number of steps that it took. So in this case, looking for a value that doesn't exist in the tree, we'll always have to visit every node in the tree. So now, no matter how big the tree is, let's say I make the tree bigger here, now it's going to take 5 steps. And that makes sense because I can't convince myself that I have the node is not in the tree until I visited every single node. Now let's look for a value that is in the tree, something like 1. Okay? So in this case, I only had to look at one node, and this is the best case of performance. This happens when the node is the root. Okay? But in general, this tree search algorithm, again, depending on what the mix is of values that I look for that are in the tree versus not in the tree, essentially has linear performance. So this is going to be O(n) in the size of the tree. So as the tree starts to get bigger and bigger and bigger, particularly when I look for values that aren't in the tree, I have to search the entire thing because I have no idea where that value might be. It could be anywhere in the tree. And this is a consequence on some level of how I built my tree. When I built my tree, there were no rules. I just put stuff wherever it seemed to fit, right? I just found an empty spot in the tree and I shoved a new node in there. Sort of willy-nilly. It didn't matter what the value of the node was. And so I didn't apply any structure when I built the tree. And so there's no structure to rely on now when I'm searching the tree. If I need to find a value in this type of tree, I have to look through every single node in the worst case because I don't know, it could be anywhere, right? And so I can't convince myself that it's not in the tree until I visited and searched every node. The question is, can I do better than this? Can I make this search more efficient? And the answer is, I can. And what I'm going to do is this requires that I change how I create the tree in the first place. So there's 2 parts to this. The first part is I'm going to build the tree differently, and I'm going to show you in a minute how that happens. The code that is involved with that is right in front of you, but I'll walk through it with you. The second thing I get to do is I get to use that structure when I look for a value. So now when I'm searching the tree, I have structure that was in the tree that I can rely on. And the idea here is when I look through the tree, I want to have some hints about where the value should be, right? And if I do this carefully, what will happen, and you'll see this, is I'll be able to search through the tree in O log n time. And log n it grows quite a bit more slowly than O(n). Okay, so how do I get this to happen? All right, so let's look at our add function. So now there's a couple of changes I want to point out. Okay, so this is another place where it pays to be comparable. Remember from our discussion of interfaces, in Java, when a class implements comparable, it means that I can take 2 values and I can compare them to each other. I can tell you which one is bigger and which one is smaller. We're going to use that when we get to sorting. But we also used it when we implemented a generic version of the maximum and the minimum that would operate on any things that are comparable. Well, here's another place we can use it. It's in our trees. So you'll notice that this binary search tree, it's a different thing than a binary tree, only can store objects that are comparable. And you'll see why in a minute. So now I can't just store any old object in Java. The object actually has to implement the comparable interface. So when I construct the tree, that's one of the times that I use comparable. And so let's look carefully at the tree construction code. So in my binary tree that we were working with up till now, when I constructed the tree, if I couldn't find a place, if the node didn't belong right there, basically, I randomly chose to put the node to the right or to the left. And that's why any value in my original binary tree could end up anywhere in the tree. Now, I'm going to do things differently. So here's what's going to happen. My add function is going to try to add the value at the current node in the tree. So essentially I start this on the root, and then my add function is also recursive. So if my add function can't find space on the root, it'll try to find another place in the tree to put that value. So here's what happens. If current is null, this means that I'm adding the root node. This is the only time this will happen based on how add is called. And so I just set root to be the new node and I'm done. Otherwise, what I do is I use the value at that node to decide where to put the new node. And so this is the code that's different. And I'm using the fact that all my values in the tree are comparable. they can all be compared to each other. And so I'm calling value.compare to value. So this is the value that's stored at this node, and I'm comparing it to the new value that I'm adding to the tree. If the value at the node is greater than the new value, then I put the node to the right. Otherwise, I put the node to the left. So at any given point in the tree, so I come to a node in the tree, and I'm essentially trying to decide where should I put this new node. So if the value that I'm adding is less than or equal to the value at that position, I put the new node to the right. I put it down here. Now, if this node doesn't have a right child, you'll see I add it as the right child. Otherwise, if it does have a right child, I still add it to the right part of the tree. Same thing on the other side. So if the new value that I'm adding is greater than the value that's already in the tree, then I put it on the left. If the current node doesn't have a left child, I put it there. Otherwise, I put it in the left part of the tree. Okay? And so by making this one change to how the tree is constructed, I can make a similar change to how I search the tree. All right, so this code already works. It will run and it will build trees, and that's all good. Oh, I need to return. Let me just add a return value so we can show that this works. Okay, so now let's rewrite our search algorithm and let's see if we've managed to make it more efficient. Okay, so now we're going to do something very similar to what we did before, which is we're going to return the result of running the search value. We're passing the same thing. We're going to restart this using our private search function, which is going to also return a Boolean. It's going to take an object value and a node to look at. And so first, let's just kind of rewrite what we had in the past. So let's say if current is equal to null, then I'm going to return false because I've reached an empty tree. An empty tree will never contain the value that I'm looking for. Otherwise, I'm going to say return current.value.equals value, or or I restart the search, current.left. I'm going to have to put this on a new line, so this is going to get too long. Or I search in the left part of the tree, value, current.left, or I search in the right part of the tree, value, current.right. Okay. And so this is still going to work. Our same algorithm, but we can do better. All right? So here's what we're going to do. We're going to say if current.value.equals value, return true. So this is also another kind of base case that we're writing. So basically we say, if the current node contains the value, I'm done, right? We used to do this as part of our OR statement, but you're going to see why we're going to move this out like this in a minute. So I've checked, there were 3 places I had to check. I've checked one of them. But now, because of how I've constructed this tree, I can tell, based on the current node's value and the value I'm looking for, where the value should be in the tree. The idea is, if I look at the current node and I look at the current value, if they're equal, I'm done. But now what I do is I compare the two. If the value I'm looking for is greater than the current node's value, then I look in the right part, well, it's either left or right. We'll figure it out. I have to go back and look at the add code. But if the value I'm looking for is greater than the current node's value, I look in one part of the tree. Otherwise, if the value is less than the current node's value, I look in the other part of the tree. And so rather than having to look in both the right and the left subtree every time, I only have to look in either the right subtree or the left subtree. Okay? So now if I go back and look at my add code, it said when the value I was looking for was greater than the current node's value, I put it to the right. And so now what I'm going to do is I'm going to say if value.compare to current.value is greater than 0, and I think this is correct, I'm going to return search value current.right. Else return search value current.left. Okay. Oh, let's see. Right, because okay, sorry. I have to change my search the signature of my search method to take a comparable. That's important. Remember, not every Java object implements comparable. So I need to change this. I do not know why this keeps happening. Okay. So now this looks incorrect. So I think I've got this backwards. So let's turn this around. Okay, so now it's right. Let's try a couple of other values here. So let's look for 5. Okay. Let's look for 1. That seems to work. Let's look for 10. That's false, right? So that works. Let's look for all the values that are in the tree. So we'll look for 3. Okay, good. So this seems to work. Now let's repeat the process whereby we instrument this to see how many steps it took. So now I'll say public int count is equal to 0. Well, I'll just set it count. I'll set it equal to 0 when I start the search. And now each time I visit a node, I'll say count plus. And then down here, what I'm going to do is also print out binary search tree count. Okay, so now it took me 3 steps to get to 3. So the first thing is, let me make a slightly more interesting tree. Put some different values in here. Okay, so there we go. So the first thing is, let's make sure that it still finds let's make sure it still finds the value that's at the root node in 1 step. So it does. Now let's look for something that's not in the tree. Okay, 10. So we look for this value 10. It only took us 2 steps to discover that the value wasn't in the tree. So that's kind of exciting. Let me look for something else that's not in the tree. Oh, well, yeah, now I can't compare an int and something else. So let's look for like 12, right? Also just took 2 steps. What about 2? That took 2. So that was true, that took 2 steps. What about 1? 1's not in the tree, that's going to take 2 steps. So before, I had to search every single node before I could convince myself that the node wasn't in the tree. And now, because of this extra structure that I've added to the tree, I don't have to do that anymore. I only have to look in certain places in the tree. And the idea is that the structure of the tree is guiding my search. So at any given point, my algorithm becomes check the current node. If the current node's value is the same as the value I'm looking for, return true right away because I'm finished, I found the value, I'm good. Otherwise, compare the value I'm looking for with the value saved at that node in the tree, because that comparison is going to lead me in the right direction. If the comparison goes one way, I go one way in the tree. If the comparison goes the other way, I go the other way in the tree. Which way I go is irrelevant. I could change things around. It has to be consistent between my add and my search, because the 2 pieces of code have to agree on, when do I go right and when do I go left. But as long as I'm consistent about it, this will work. Okay, so now let's think about how long this will take to search, and we're just going to make a general argument here. We're not going to get too specific. So here's the idea. At each point in my algorithm, let's say I have a tree, and let's say that roughly the tree, every time I look at a right and left subtree, they're about the same size. Now, this is an important assumption, and when you get to 225, you're actually going to spend a lot of time learning how to keep trees balanced, is what they're called, okay? Because if I look at an unbalanced tree, it turns out that this search algorithm it could be as bad as ON. But on a balanced tree, and a balanced tree means at every point in the tree, if I look at a node's right and left subtree, they're about the same size. In a balanced tree, this algorithm will typically run an O log n. Why? So again, let's think about what's happening. At every given point in the algorithm, I do 2 things. One is I check the current node, and the other thing is I make the problem smaller. But here, the idea is I don't have to look in both the right subtree and the left subtree. So if I start with n nodes to look through at the very top of the tree, at the next stage of my algorithm, I only have n over 2 nodes because I'm only looking on the right side or the left side. At the next step in the algorithm, if I didn't find the node, I only have n over 4 nodes to look through, right? Because I only have to, look at one side. At the next step in the algorithm, I only have n over 8 nodes to look through. And what we discover is when we are, whenever we have an algorithm that makes the problem about half as small in each step, that algorithm has O log n runtime, meaning that as the problem gets bigger, the amount of steps it takes grows much more slowly than the size of the problem, right? Because at each step in this algorithm, we're making the problem about half as small. Now again, there's a bunch of caveats here, and you guys will learn more about this as you get on into later classes. But I couldn't resist kind of showing you this because it's a really neat application not only of the tree type data structures that we've been talking about, but also this comparable interface that we brought up. Another place where it pays to be comparable. It pays to allow two instances of your class to be compared with each other, because now one of the things I can do is build a binary search tree that allows me to do search much, much more quickly. Okay, cool. So let's go on. So now let's do another tree-based problem for fun. Let's look at let's look at an algorithm where we're looking at all the nodes in a tree. And what we want to do is this is sometimes called flattening a tree. We want to take this hierarchical data structure and convert it into a list. Now remember, before when I said that all of the recursive algorithms we implement on trees, we could also implement them iteratively. And this is one of the places where we can create a bridge between these two worlds. So we have these trees that we've been writing these recursive algorithms on. So, when I counted the number of nodes in the tree, I wrote a recursive algorithm to do that. When I searched through the tree, I wrote a recursive algorithm to do that. Can I write iterative algorithms to do those things? I can. And in many cases, the first step in those iterative algorithms is convert the tree to a list of nodes, at which point, for example, if I wanted to search, I just go through the list one at a time and look for the value. If I wanted to count, I just look at the length of the list. So how do we take a tree and convert it into a list? So here we're going to use these lists that you guys are already familiar with from your previous work on the MP, lists as a built-in data structure in Java. You guys have implemented lists, so you've seen behind the curtain here. You know a little bit about what's happening internally when a list adds elements and stuff like that. But right now we're not going to use our list. We're actually just going to use Java's built-in lists, right? And we're going to use them to build up a list of nodes that are in the tree. And so how do we do this? So essentially, again, whenever we get to a null node, that means we reach an empty tree. An empty tree has no more nodes that we need to add to our list, and so we're done. We just stop. Otherwise, we look at the right and left subtree separately. So we need to add all the nodes in the right subtree to the list and all the nodes in the left subtree to the list. Those are our steps. The way we combine the results, this just sort of happens naturally. We add ourselves to the list of nodes, and then we also add all the nodes in our right subtree and all the nodes in our left subtree. So to do this, again, we're going to use this built-in list in Java. Lists are tremendously useful data structures. You guys have some idea about how they work because you've implemented them. Now we're going to just use them because they're tremendously useful. I'm not going to go through this. You guys have seen this on the MP and stuff like that. Some semesters, the MP list usage was still after this point in the class. This semester, you guys are old hat with lists because you've been using them for the past couple of MP checkpoints. So I don't feel the need to go into to detail about that. All right, so let's go so now we're back to our old binary tree that was just built at random. But what we want to do is we want to take our binary tree and return a list of all the values in the tree. Okay, so now again, we do this in a very similar way than we did in the past, although this is a little bit more interesting, okay? What we're going to do is our private helper function here is not going to return a list. It's going to return void. It's going to take as arguments a node to add, and then also a list of the previous values in the list. A list of the values that have already been added to the tree, okay? So we'll call that values. What we're going to do in our wrapper function is we're going to create a new array list. So we're going to say list values is equal to new array list. And then we're going to pass that list to we're going to run our recursive function, all values, root values, and then we're going to return the list that we created. So again, this is a little bit different. In this example, the wrapper function is doing a little bit more work. The wrapper function is actually what's going to initialize the list, create the list for us. When I create a list, it's always empty to start with. Then I'm going to pass that to this all values function that's recursive, and it's going to, as it runs, add items to the list. Then once add values completes, I'll have a list, assuming that I implement add values properly, that contains all of the values in the tree. Note that I want to add the values, not the nodes. All right, so let's give this a try. So our base case, as it frequently is the case where current is null. That means we've reached an empty tree. There are no values to add here, and so we don't need to do anything. We just return. Otherwise, I need to take the list, and I'm actually going to go, you might ask, well, how do I know how to add things to a list? Well, I'm going to go back here, and I'm going to look, okay, so there's an add method that lists support. This is very similar to what you guys already did. I don't think the problem said that I had to add them in any particular order, so I'm not too worried about where this value is going in the list. So I add the value that's stored in this node. And then all I need to do is I need to run add values on my right subtree. I need all values. Yeah, all values on my left subtree. So these are my recursive steps. The combining results together is happening as we go. So essentially the way I'm combining results together is I pass the same list to both my left and right subtrees. So imagine, again, the wrapper function creates an empty list, and then the wrapper function hands it to the first call to all values. That call adds itself. It passes the list that now has one element to its right subtree and to its left subtree. And either those calls start to add their values, et cetera, et cetera. So this goes all the way down until I get to the leaf nodes, and every node in the tree has been added. All right, so let's see if this works, and it seems like it does. So I've created a tree. Let's make sure it works with an empty tree. I get an empty list. That's what I expect. Let's put some items in the tree. Now you'll notice the items are not necessarily in the same order as they are, because the order in which they get added to the list depends on where they are in the tree, and their position in the tree is random. So if I run this a couple times, you'll see that 10 is bouncing around. Sometimes it's at the end, sometimes it's up in the front. It just depends on where 10 ended up in this tree that I built randomly. Okay, so, and this is an example of a case where, it's a little bit more of an interesting spin on some of the recursion we've done in the past. It's using a list as a new data structure. And so, for example, again, let's say I wanted to implement a search on top of my tree, right? Another way to do that would be as follows. So again, this is my bridge between the recursive world of working with trees and an iterative world of working with trees. So another way to implement search, I'll just do this right here. Public Boolean search, pick a value, is to say list values is equal to all values. Right? So I basically call all values on myself. That gives me a list of values to look through. And then I say for value in values, sorry, I need to use, this is object value values. Oh wait, I don't want to use this. Call it value in list if value dot equals value in list, return true. Otherwise, I keep going. Right. Otherwise, I return false. So if I go through the entire list, I don't find it. Again, I'm not sure why this is happening. Better. Okay, so now what I can do is I can say system.out.println binary tree.search, and I'll look for like 9 or something else, look for 6. 6 in the tree? No. I think I need another semicolon. There we go. Let's look for 2. 2 is in the tree. And so again, I promised you that everything I could do on a tree recursively, I could also do iteratively. Here's the bridge. Here's the thing that brings them together. So now what I've done is I've written an iterative search function. This is, the runtime of this is identical to our old search function, except what it does is at first it flattens the tree into a list, and then it goes through the list one step at a time. So recursive search, we did at the beginning of the class. Iterative search, I do by way of a function that converts everything into a list. Okay, let's sally forth. Move on and talk about some other things. One of the things I want to make sure I point out before we move on We may not get to an introduction to sorting today, and that's totally okay. We'll do it on Friday if we don't. One of the things I wanted to get to is this idea that recursion is not just something that's confined to trees. We're actually going to work with recursion a little bit later in the semester on arrays. But recursion is a broad problem-solving technique that can be applied in a lot of places. And it can be particularly applied on data structures, where each part of the data structure is also an instance of that data structure. We exploited this when we looked at trees. If I take a tree, at any given node, the right subtree and the left subtree are also trees. And so the idea was I had this nice way of taking a problem using recursion and identifying this self-similarity with the tree data structure and saying, okay, well, if I don't know how to count all the nodes in the tree, what I'll do is I'll split the problem into counting the left subtree and the right subtree, and both of those are trees. And so I just restart my algorithm on those trees, and I just need to know how to combine the results together. The question is, are there other data structures we've looked at that have this property, where every part of the data structure is also an instance of that data structure? And it turns out that a list that we've already looked at is a data structure that you can do recursion on. So think about a list, right? So a list, if I break a list into two pieces, both of those are lists. And so it's possible to write algorithms that operate on lists that are recursive. An array is also a recursive data structure, right? And by contiguous, I mean, when I break these up, like if I take an array, if I take all the even elements, well, that's not another array, it's something weird, right? But if I take an array and I divide it in half or into like two contiguous pieces, so if I take the first four values and the rest of the array, both of those are smaller arrays. And so I can write recursive algorithms that not only run on trees, where they tend to be very useful, but also that run on other data structures as well. Lists, arrays. I'm not sure we'll do anything with lists this semester, but we will come back when we talk about sorting and get to recursion on arrays, because it's useful in the context of implementing some of our sorting algorithms. List recursion, so again, each part of a list is also a list. Right? So if I take a list and I look at one element and the rest of the list, then I can apply the same thing, right? So let's say I'm searching for an item in the list. So I say, well, I don't want to iterate through the list because I'm trying to solve this recursively. And so what I do is I look at the current element, the current item, and I say, does the current item contain the value? If not, then I look in the rest of the list, right? So here I would say, let's say I'm looking for item 0. I say I'm at the start of the list that contains the value 6. I say, okay, well, 6 isn't equal to 0, so I need to look through the rest of the list. And then I restart my algorithm on a list that starts with 5. I say, does 5 equal to 0? No, okay, well, it has to be in the rest of the list, right? So now I restart my algorithm on 8, and I repeat that process, right? So with lists, just like with trees, I need to both have a way to make the problem smaller and identify the smallest subproblem. How do I make the problem smaller? I divide the list into two parts. And frequently what I do is I look at the current item and the rest of the list. So the current item is a list of size 1. The rest of the list is a list of size n minus 1, where the list that starts at the current item has n elements. So I've created a smaller problem to solve, right? What's the smallest subproblem that I'm going to solve when I do recursion on lists? It's typically a list with a single element or an empty list. If I'm searching a list, for example, when I reach an empty list, I know that an empty list doesn't contain the value that I'm looking for. And if I'm looking at a list with a single element, it's very easy to search because I just compare the value of that element to the value that I'm looking for, and I get either a true or a false. I can also do recursion on arrays. And this is something that we will come back to, but I just want you to see how this would happen, right? So again, let's say that I'm searching for a value in an array. I can take advantage of the fact that each part of the array is also an array. So let's say I'm looking for a value in this array. I basically break it into two smaller arrays, one at the beginning and one at the end, and then I continue this process. I can take the first smaller array and break it into even smaller arrays. This one has two items, and then I take that small array and break it into smaller arrays, and finally I get to the point where I have one item, and then I can just directly compare the item I'm looking for with that item. This is sort of a version of the phone book example that you might have seen in online when people are searching for things, right? So when you're looking for a name in the phone book, what do, right? Well, I open it to the middle, and then I decide, okay, well, is the name I'm looking for to the left or the right? Now this works because phone books are sorted. So the idea is I open to the middle and I say if the value that I'm looking for is to the left, I've made the problem half as large because I can ignore the rest of the phone book. But the nice thing is that first half of the phone book is still a phone book. It's sorted exactly the same way. And so I can repeat that process. I can take that part, divide it in half and say, is it the first half of that phone book or the second half of that smaller phone book? And I repeat this process over and over again until I find the exact page that I'm looking for and the entry that I was searching for. So array recursion, what's our approach here? How do I make the problem smaller? I look at two smaller subarrays. Sorry, break the array into two smaller subarrays. How do I identify the smallest subproblem? This is an array that's either empty or has a single item. And that's usually a very easy array to work with. All right, so I'll take questions about recursion on the forum. Otherwise, so here's what I'm going to do. I might finish a few minutes early today, which I think is fine. Sorting, what we'll do is we'll come back and we'll talk about sorting next time. What I want to do is talk a little bit about the final project. Now, in a normal semester, we would be in the midst and very excited about planning a final project fair for all of you. And that is clearly something that's not going to happen this semester. We won't be able to be all together in May. The final project fair is usually my favorite thing that we do every semester together. It's super fun. You guys get to build some really cool things. I'm always super blown away by some of the neat final project apps that teams put together. I want to preserve as much of that as possible. I know that these are difficult circumstances. I know that we're all distributed all over the place. I know that you guys may be distracted by other things, other classes or whatever. But I do still want to really encourage you to do a final project. We will have a way for you to share that with the rest of the class. We will still put those final projects up on display on the website. And to the degree that I have any power to promote the amazing work that students in this class do every semester, I will do that. Okay, why are we doing this though? So, one of the reasons that we do a final project in this class in the first place is to try to help prepare you to have a meaningful and exciting career in technology. Because here's the thing, if you come into our program and you take some classes and you get good grades, that's not going to necessarily lead you in the direction of getting a great CS job or having a meaningful career in technology. So again, this is what, too many, I would argue, of our students do. They take classes, they do what they're told to do. They get good grades. They get good grades based on doing the things that we told them to do. And don't get distracted by all the other cool stuff that's going on there in the world of technology, because that might cause your grades to suffer, right? So don't do any side projects. Don't try to learn something on your own. Don't get sucked into something that started off as a hackathon project that you then want to try to turn into a real app. Just, focus on getting those grades, right? Because that's the most important thing. But here's the thing. If you walk up, you see the lines at the career fair. You know how many people in those lines have a transcript that looks exactly like yours is going to look like if you pursue this strategy? You'll have, a whole transcript full of pointy letter grades and CS blah, 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 and CS blah, 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 and CS this and CS that. But that doesn't show any passion. That shows this cold, calculated, I think I'm trying to do what the employers want me to do sort of attitude towards things, right? And if you want a great CS job, or again, maybe this is too focused on jobs. If you want a meaningful and, special, right? If you want this to become a vocation, if you want, you need to show your passion for technology, and you need to allow yourself to explore, to try new things, to fail, to freak out, to get in over your head, to pick up something that might end up being too hard for you to do and take a stab at it. That's a really important part of learning and growing in this field. Our final project is really intended to try to get you started doing that. So, students, when they come to me, they say, well, how can I get a job when I graduate? How can I make sure that I have a meaningful career in this field? I say, what you need is not a transcript. You need a portfolio. A portfolio is sort of like what an artist might produce over their time as an undergraduate. When you go to the career fair If instead of just shoving the same transcript in front of the recruiter that they've seen all day long, if you can say, hey, I built this cool new app that's up on the App Store and I've got 1,000 users. Or you can say, hey, I built my own Lisp interpreter because I wanted to learn Haskell. Or if you can say, I built my own operating system because I wanted to learn Rust. Like, these are actual real projects that I know that students have done. That's gonna, the person who's been, sitting there all day long looking at the same, I got an A in 225, I know how to do AVL trees. Like, they're gonna perk up when you show them something special like that, when you show them something unique, when you show them something that shows that you stepped outside the bounds of what you were forced to do, right? No one forced you to do that, right? No one required, it wasn't part of a class project or whatever that, you built this thing. You did it because you wanted to and because you wanted to learn. And along the way you did learn and you've showed a passion for technology because employers know that that's what they're hiring, right? They're not hiring your knowledge. You think what you've learned in college is sufficient to prepare you for, even a decade-long, much less a multiple decade-long career in technology? That's insane. This stuff changes all the time. I mean, I've learned 10 times more in the 10, 15 years that I've been out of school as I learned when I was in school. And you've got to keep doing it. You have to keep learning and growing along the way. Showing people that you're willing to do that will excite them. And they will think, hey, now I'm hiring someone who a couple years from now is going to come to me and say, hey, I found this cool new way to do things because I was, reading articles online. I think this could be a great fit for our company. Why don't we try it? Rather than just being like, okay, well, what did you tell me to do today? I'm going to, bang out some more Java code or whatever. Right? It's not fun. It's not exciting. It's not really what technology is. So the final project in this class is open-ended. It's generously graded. It's collaborative. We're going to have you guys work in teams. You guys will get a great chance to practice working in virtual remote setting due to the circumstances. I think that's actually going to be pretty useful. And it's really designed to be a springboard. Some people take it, right? Some people take it and they do things that end up as part of their portfolio years later. And if you do that, you don't have to tell anyone that it was a 125 class project. Don't do that, right? Be like, hey, I built this cool app and now it's up on the App Store. I don't care, right? I'm not claiming any credit for anything that you do. I'm hoping that this gets you started. There have been some real cool apps and projects that have come out of this class that have gone on to become more real things in the future. And so that's our goal, right? But really, it's designed to give you practice of just the process of even contemplating something like that. You felt the need to do something. You thought there was a cool new app that deserved to exist in the universe. How do you even get started, right? From scratch, from a blank screen, basically. Some of you will take this and really run with it, right? Some of you, won't get as far. Some of you will, right? And that's cool too. Like, failing and having a project that you kind of don't have to really be too invested in is a really important part of preparing you for the day that you do have something real that you want to build and you're excited about. So, just to kind of show off, here's some of the, projects from last semester. This is up on the website. You guys can browse through these. Again, as always, we have people do some really cool things. We still will have awards that we'll give for some of the best projects that also get sort of, primary primo placement up here on the website. So there is, some incentive for those of you that have some time and energy and want to start the next step on your journey in computer science, and particularly the next step on your journey toward independence and towards being able to do your own things and learn on your own and pick up stuff that you're never going to be taught in class. And that's the goal of this part of the course. All right, so I've done a few minutes early. That's totally okay. I've got office hours today from 4 to 5. Please stop by and say hi. The link is already up on the website. If you have any concerns about things right now, please let me know. As always, I hope you guys are staying safe, taking good care of yourselves, taking good care of the people around you, thinking about how to reprioritize things so that you can do whatever's required at this time. I know some of you guys are going through really rough times, and I'm sorry about that. I hear stories from people, and I get it, right? I mean, it's scary for all of us, but it's harder on some of us than on others. So I wish you guys all the best. I will look forward to seeing you again on Friday.